Last lesson we looked at exponential functions and graphing. Today we'll look at logarithmic functions. Do find that they require a little bit of thinking, but I'll try to show you a technique that makes sketching them a hell of a lot easier. So if we've got the graph of y equals log 2x, then note that that can be written in exponential form. We can say that that's 2 to the y equals x. Okay, so 2 to the y equals x. All right, and we know that that's the same as that. If we swap x and y, i.e. find the inverse, then we get y equals 2 to the x. So it's important to note that the graph of y equals log 2x is a reflection along the line y equals x of the graph of y equals 2 to the x. And you can see that there. Okay, so here's 2 to the x with its coordinates. And note that on 2 to the x is the coordinates 2, 4, and on its inverse is the coordinates 4, 2. Notice that they flip, they swap, and they swap. Okay, so that's all a logarithmic graph is the inverse of an exponential. Okay, and note that because a log graph is the inverse of an exponential graph, the domain and range swap. Right, so let's find the inverses of the following, and let's assume that we'll state the domain of the inverse. Do not wait to be asked. So if we're inversing this, let's just first of all consider the exponential function. It's 4 to the x, goes 3 up, like so. Right, so the domain of the original function is all real numbers. The range of the original function is, what's it going to be? 3 to infinity. All right, so let's say let y equal 4 to the x plus 3. Now we're going to say for inverse swap x and y. So we're going to go x equals 4 to the y plus 3. All right, now what we're going to do is go x take 3 equals 4 to the y. We need to make y the subject. How are we going to do that? Well, let's switch it to log form. So we're going to say that log 4 x take 3 equals y. So there's our inverse function. So let's write that with full function notation and say that that is f negative 1 is a function such that its domain, well, what's its domain going to be? The domain is going to be the range of the original function, so 3 to infinity, maps to the codomain, which is a set of all real numbers, f negative 1 x equals log 4 x take 3, and there it is. Right, let's do this one here. So we want to inverse the logarithmic function. What we're going to get is an exponential function. Over here we inverse an exponential function. What we have to get is a log function. We're going to say, let's do the domain first of all. So the domain is, now this one here is, or you might find this a little tricky. I know how to actually visualize that. That log function there is moved 5 units to the left. So it looks like that. So its domain is going to be from negative 5 to infinity. Its range is going to be the set of all real numbers. Okay, so let's say let y equal g of x equals log e x plus 5, take 2. Right, so we're going to say swap x and y. So next up we're going to say x is equal to log e y plus 5, take 2. Right, let's add 2 to both sides. And now let's change the form. So we're going to say that that is e to this index here, x plus 2 equals y plus 5. Y is equal to e to the x plus 2, take 5. Right, let's write that full function notation. F, no, it's not f, it's g, I think. G negative 1 is a function such that it has a domain, which will be the range of the original, which we know that exponential functions have a domain of all real numbers unless it's been restricted. So we didn't need the brackets for that either. Real to real, g negative 1 x equals e to the x plus 2, take 5. Okay. sketch the following. Okay, so it's very important to note what the basic log graph looks like. So y equals log 2x, okay, is going to look like this. Right, so that's what the basic logarithmic graph will look like, where its intercept is going to be when x is 1, y is 0. Now again, why do I know that? Well, think about its inverse function, which will be an exponential function. So 2 to the y equals x, swap x and y, 2 to the x equals y. So there's its inverse function. Its inverse function will have a y-intercept when x is equal to 0. That's y equals 1. So when x is 0, y is 1 on the original or the exponential function. So the log graph will have a y-intercept there. All right, so here's how we sketch logarithmic functions. Oh, and I forgot a really important point here. It has an axis, an asymptote at y equals 0, because the original function has an asymptote at x is equal to 0. So what happens when you swap x and y is the asymptote also changes. Right, so let's go through it on this function here. So what we're going to say is that the asymptote, which would be originally at y equals 0, will now move to 3 units over. So it's going to be an asymptote at y equals 3. All right, now what will be the y-intercept, or the x-intercept rather? So this x-intercept here will also move 3 units over. Okay, so it originally would be at 1, 0. It's going to end up at 4, 0. So there's 1, 2, 3, 4. That's where it's going to be. And that's what our log graph will look like. Right, now the other way to work that out is that we put in, so we're going to say what is the x-intercept? The x-intercept occurs when y is equal to 0. So 0 equals log 2 x take 3. 2 to the 0 is 1 equals x take 3. After I change the form, x is equal to 4. So you can tell when x is equal to 4, y is equal to 0. All right, this next log function is y equals log 2 x plus 2. So again, we know that the basic log function has an asymptote at y equals 0. This one here is going to move the standard logarithmic function 2 units to the left. Okay, that's what that will do, is 2 units to the left. So we're going to go and put our asymptote there at y equals -2. All right, now what's that going to do to the y-intercept? So the y-intercept, or the x-intercept rather, is usually at 1, 0. It's going to move it 2 units to the left, so it should be at -1 also. Now let's just check whether that's right by going 0 equals log 2 x plus 2. 2 to the 0 is 1 equals x plus 2, x is equal to -1. So yeah, definitely when x is equal to -1, the y value is 0. Okay, let's find out the y-intercept. So the y-intercept occurs when x is equal to 0. So I'm going to do f of 0 equals log 2, 0 plus 2 is 2. Log 2, 2 is equal to 1. So it's got a y-intercept of 1 as well, or not as well. Okay, so now let's draw our logarithmic graph. Remember, needs to exhibit asymptotic behavior, and then it will go something like that. Let's label these with coordinates. So this one here should be 4, 0. This one here should be -1, 0. That should be 0, 1. Okay, so some transformations use mapping to show that when f of x equals that is dilated by a factor of 1/3 from the y-axis, the equation will be this. Okay, let's do it. X comma y maps to, and 1/3 from y changes x, that's x on 3 comma y. That's x dash, that's y dash. Original function is y equals log log 2x, so we need to make x and y the subject. X dash equals x on 3, y dash equals y. 3x dash equals x, and now let's substitute into that. So we're going to have y dash for y equals log 2, 3x dash, or y equals log 2, 3x. Therefore, f of x equals log 2, 3x. In fact, I don't really like that. So use mapping to show that this, when dilated, is this. It really should be a different function. You can't dilate a function and create a function of the same name. So let's just call that g of x, call that g of x. Okay, so what we'll do is sketch the graph of that. See? So we've got our original log function here, and there's no translation left or right, so that'll leave the asymptote sitting right in that spot there. And we're going to note that the x-intercept occurs when y is equal to 0. That's 0 over here. 2 to the 0 is 1. 3x. Let's just try that again. So we're going to go 0 equals log 2, 3x. 2 to the 0 equals 3x. That's 1 equals 3x. X equals 1/3. So when x is equal to 1/3, the y value is 0. So here it is there, 1/3, comma 0. Draw something, whoopsie, that looks logarithmic. That'll do. Okay, so a really difficult log to sketch here. Let's have a go at this one now. My recommendation is that we sketch it via transformations. So we need to think about how we get from f of x, or should I say y equals log 2x to y equals negative log 2, 4 take 2x plus 1. Okay, so let's put our dashes and our dashes. All right, let's set this one up for pairing. Y dash, what's it going to be? Take 1 over negative 1 equals log 2, 4 take 2 x dash. All right, now this is ready for pairing, so we're going to say that y equals y dash take 1 over negative 1, and x equals 4 take 2 x dash. All right, now let's work out what the transformations were by going and subbing for x dash and y dash. So let's do x dash first of all. So we've got x take 4 over negative 2 equals x dash. X take 4 over negative 2. Y dash is going to be negative y plus 1 equals y dash. So negative y plus 1 equals y dash. Okay, so our transformations, let's look at x first of all. So it's trans for left reflected in the y-axis, and it is a dilation half from y. Okay, what next? Let's look at y. It's reflected in x-axis, and it's trans 1 up. All right, now, why did we do this? Here is our standard function. What happens? It gets translated 4 to the left. So there's the asymptote there. So the asymptote's going to go 4 to the left. So that's what it looks like. Reflected in the y-axis means that that goes 4 to the right. And what's going to happen? It'll sort of go like that. Dilation half from y. So that value there will half, and so will the asymptote. So the asymptote is going to be at y equals 2, and we'll get our function that looks like that. And then finally, reflected in the x-axis means that that will flip, so it's going to come asymptote in the same spot, but it will sort of go like that, and then up 1. So it's going to come up 1 higher than that. Right, so what do I know? I know for a fact it has a x-intercept and a y-intercept. I know that the asymptote is going to be at y equals 2. Let's just try it. So we'll put, that should be x is equal to 2. We'll put x is equal to 2 in there. 2 times 2 is 4. 4 take 4 is 0. Log 2, 0 doesn't exist. Okay, now let's work out what our x-intercept is. Let's go y-intercept first. So we'll go f of 0, which is our y-intercept, negative log 2, 0 goes in, 4 plus 1, f of 0 equals, that's going to be 2 raised to what power gives me 4? The answer is 2. Negative 2 plus 1 is negative 1. So our y-intercept is at negative 1. There's my version of it there. Didn't quite work out right. Okay, it looks like it is above the x-axis there, but that's okay. I know what the general picture looks like. So I'm expecting an x-intercept somewhere around about there. So we'll go x-intercept, y is equal to 0. 0 equals negative log 2, 4 take 2x plus 1. Negative 1 equals negative log 2, 4 take 2x. 1 equals log 2, 4 take 2x. 2 to the 1 is 2 equals 4 take 2x. Negative 2 equals negative 2x. X is equal to 1. So there's x is equal to 2. So looks good. Okay, I did expect something like that. Right, if you look at the shape there, you can tell that this log function will come up, go through that point there, come up, and exhibit asymptotic behavior. All right, so that's 1, 0, and 0, comma, neg 1. Got the label there. Yep, all good. Okay, so find the equation of the image of this after it undergoes this stuff here. So let's actually do, in inverted commas, the stuff. Reflection in the y-axis changes the x value. Horizontal translation will be negative x plus 2, comma, y. Dilation 1/3 from x changes the y value. Negative x plus 2, comma, y on 3. That's x dash, that's y dash. X dash is equal to negative x plus 2. Y dash is equal to y on 3. Okay, so what do I need to make the subject? Well, we've got a y and an x, so I need to make y and the x the subject. 3 y dash equals y. X dash, take 2 all over negative 1 equals x. Okay, so now what we'll do is just note that this could also be written as negative x dash take 2 equals x, or I could write it as 2 take x dash equals x as well. Okay, so let's rewrite our functions. So 3y dash goes on for y, log 2, and x gets 2 take x dash. Let's write that as y equals 1/3 log 2, 2 take x. And let's put a domain over which people are allowed to use this rather than imply it. So we're going to say 2 take x must be greater than 0, negative x must be greater than negative 2, x is less than 2. So we're going to say where x is less than 2. That's when I'm letting you use it. Right, so there are the problems for today's class.